before Sibylle starts the lecture, I just want to remind you that today we will only have one lecture, and then we will have the socialization session afterwards in Gathertown. So yeah, I recommend all of you to attend. Then yes, if you want to ask questions, you should do this in the chat during the talk. And then yes, we will also post the slides of the talk in the chat. So with that said, it's my great pleasure to introduce Sibylle Schroll, who will give her last lecture on the bounded derived category of a gentle algebra.
Thank you very much, Sandra. Okay, so I want to start with a very brief recall of what we've done so far. So we started with a gentle algebra. From that gentle algebra, we constructed a ribbon graph. And that ribbon graph then is a deformation retract of a surface that's unique up to homeomorphism in such a way that the faces of the ribbon graph are in bijection with the boundary components of the surface. Once we have that, well, then we also saw that the gentle algebra gives us sort of a way to glue the vertices of that ribbon graph onto the boundary. And once we have the ribbon graph embedded in the surface in this way, we can construct a dual graph of that ribbon graph. And this dual graph, in some sense, encodes the projective indecomposables of the algebra. And then we saw that the surface, the dual ribbon graph, and the vertices of this graph and the punctures in here, or the vertices in the interior in there, give us a geometric model of the bounded derived category of a gentle algebra. And here is that model. So this is the ribbon graph of the gentle algebra, which is just the A3 quiver embedded in the surface. And then here is the dual graph with four vertices. And I have written, I have sort of drawn in green all the indecomposable objects up to shift in the bounded derived category. So they're given by connecting black mark points. And if you remember, the indecomposable objects in the derived category are given by graded homotopy strings. So a homotopy string was a sequence of arrows and formal inverses, and then we put a grading on there. And associated to a homotopy string or graded homotopy string, we define a complex. And this complex corresponds to a green arc with a grading. And if you remember, with a green, with the grading sort of was given by, for example, here, by counting or how many black mark points are on the left and on the right when I go along a green arc from right polygon to right polygon. Okay, so that's the model for the bounded derived category of a gentle algebra. And then today I want to explain, as far as I understand it and as best as I can, the relation to the partially wrapped Fukaya categories of surfaces with stops. So that's the next section, partially wrapped Fukaya categories of surfaces with stops. Okay, so this is work by Haiden, Katzarkov and Kontsevich. It's was on the archive in 2014, and they give themselves, they start with a Riemann surface S, but really I think they can just start with a topological surface or with an oriented compact surface with boundary. And this surface has stops, what they call stops, and they denote them by sort of strips of boundary segments, or yeah. And we can think of these stops as marked points in the boundary. And we'll also ask that each boundary component has at least one stop. Okay, then they equip the surface with a grading structure. And that grading structure is the data of a line field. And so surface given by a line field. And by definition, a line field is a section of the projectivized tangent bundle of the surface. So that means that we, to each point in the surface, we pick out a tangent line, and that tangent line is now in the projectivized tangent bundle. So you can kind of think of it as not being oriented. Okay, and what this does, it gives us a winding number, and the winding number of the line field gives a grading on curves in the surface. And furthermore, then we look at Lagrangians, and the Lagrangians in the surface, of course, are half-dimensional, so they're just curves in the surface. Okay, and now, well, there are many results in this paper by Haiden, Katzarkov and Kontsevich from 2014, or it's published in 2017. But one thing they do, they construct a partially wrapped Fukaya category on such a surface. And they tell us what a generating set of that Fukaya category is. So they say a set, L1, up to Ln, of non-isotopic, pairwise disjoint, graded Lagrangians. Okay, so they sort of, they can start, there can be closed curves, or they can start and end at the boundary, but not on the stops. And they generate what is called the partially wrapped Fukaya category. And I mentioned last time briefly that this was introduced by Oru. And we'll denote that Fukaya category by W, S, M, and eta, where M is our set of stops, S is the Riemann surface, and eta is a chosen fixed line field. And they generate this category as a triangulated category. If the complement of the Lagrangians in the surface, so it should be the union of the Lagrangians, is a disjoint union of open disks, let's call them dk, where each dk has at most one stop on the boundary. Okay, so this is a generating set, but the corresponding A infinity algebra might not be formal, so there might be higher multiplications, and they give a criterion of when this A infinity algebra is actually formal, namely if each dk has exactly one stop in the boundary, then the A infinity algebra, which is given by, it's given combinatorially really in their paper. Okay, so they take the sum of hom Li Aj. So basically, I'll do an example in a moment, but they combinatorially construct the elements in here, and then they get this A infinity algebra, and then they put a more remark, and I mentioned this also last time very briefly, that using a similar proof as the proof that Abazaid gave for the infinite global dimension case it shows that this is actually the Fukaya category, the partially wrapped Fukaya category of a root. So in some sense, then this is the Floer chain groups and the bordered Heegard-Floer homology that gives rise to the partially wrapped Fukaya category. But the way that Haiden, Katzarkov, Kontsevich constructed is really completely combinatorial or topological, and they also show the A infinity structure that way. Okay, so anyway, so if each of these disks has exactly one marked point or one stop in the boundary, then this A infinity algebra is formal, and it is derived equivalent to the perfect derived category of a graded, well, of a homologically smooth graded gentle algebra with zero differential. Okay. Okay, in particular, if the line field is such that A is trivially graded, then we get that this partially wrapped Fukaya category is derived equivalent to a Genta algebra of finite global dimension. Okay, so this is nice, but maybe we should have a look at the model and see, because now we have a geometric model here, and this is given also in terms of a surface dissection, as we see by this here. And so let's compare them. So the example I want to do is the example we just looked at, namely the A3 quiver. Ah, well, okay, so in disguise. But this is not how Haiden, Katzarkov, Kontsevich start. So what they do is they start with a surface. And here I'm going to take a disk. And on that surface, they have some marked points, which they call stops, and they depict them by lines. And then they choose a line field, and for the moment we're going to ignore that. We're going to have a look at that later. But then they choose a set of generators that can start and end on the boundary, but they start and end on the boundary, but not at the marked points. And here I've chosen these. And we can see that the complement is a disjoint union of disks. And I have chosen them in such a way that each of the polygons that it cuts out has exactly one stop on the boundary. Okay, so this tells us that the corresponding A infinity algebra is formal. And we therefore have that L1, L2, L3 generates the partially wrapped Fukaya category of this disk with these 4 stops and then some line field which we haven't specified. And therefore, this is derived equivalent to the perfect derived category of some Genta algebra. Now, what is that Genta algebra? So this Genta algebra really is given by this space here. And this space here comes from this flow on the boundary. It's called a reed flow. And the stops really stop it. And I suppose that's why they call them stops. But these are the elements. So A is in Hom, L1, L2, and B is in Hom, L2, L3. And actually, because we can continue this flow here, we have that AB is non-zero. And so this means we get exactly this Genta algebra with A and B, but it has some grading on it, okay? And now there is a line field on that surface such that, okay, so let me make some room. Such that, so if we have a line field, if eta is such that the degree of A is equal to the degree of B is 0, then this is of course the category we saw earlier, okay? And now what are the remaining Lagrangians or homotopy classes of that? Okay, so what other curves do we have? We have this curve, and we have this curve, and we have this curve. So we really find that fundamental domain of the AR quiver here, which is the same objects as above. So up to shift, these are the indecomposable objects in the derived category. But really the Fukaya category does not depend on the generator. So we would get exactly the same Fukaya category or an equivalent Fukaya category if we had started, for example, so we take the same surface, we take again the stops, and now we choose different generators. So we could have chosen S generators, for example, this guy here, and this guy here. So we still have that flow on the boundary. So let's call them L1, oops, L2 and L3, and A and B. And then here we get that if we fix some line field, and then this is derived equivalent to this category here, where we again have some grading on the arrows A and B. Okay, and of course we know that for the right gradings, and here I guess we can't see it, but if we have the same line field, we get good gradings. We know that these two algebras are derived equivalent to each other. Okay, and you can kind of see that if you add to the surface the Lagrangians which are missing, which is this one, and this one, and so you see you get the two categories have exactly the same objects up to shift. Okay, so the thing we have not talked about is the line field, and in some sense, but what this example I think already shows is that we can see derived equivalences of Genta algebras through these Fukaya categories. And this is what we would like to look at closer, and what we did in joint work with Claire Amiot and Pierre-Guy Plamondon. Namely, we want to construct a derived invariant for Genta algebras, and we would like it to be complete, because then we know it, well, differentials, of course, Genta algebras up to derived equivalence, but really it also does the same for the Fukaya categories. Now, we can do that only in the zero graded case at the moment, but it should be true more generally. Okay, so what do we know about derived equivalence classes or derived invariants for Genta algebra? There's one that has been much studied, that's been introduced by Avella-Alaminos and Geiss. Okay, so they did define a derived invariant, which we'll call the Ag invariant. So again, A is gentle throughout the section. So Ag of A is a map from n cross n into n in terms of permissible and forbidden threads. And then they show that if we have that A is derived equivalent to some other genter algebra B, then they have the same Ag invariant. Okay, so this Ag invariant is encoded in the surface, and instead of defining permissible and forbidden threads, we can just see what it is on the surface. And this was at the same time in a paper by Lekili and Polichuk, and then in a joint work with Sebastian Opper and Pierre-Guy Plamondon. Is this description of the Ag invariant. So suppose that the boundary has n components. Then the Ag invariant counts the number of pairs of the form xi, yi for I from 1 to n, where xi is simply the number of marked points on the boundary component bi, and then the yi is li minus xi, where li is the number of red half edges incident with the boundary component bi. So the red half edges, of course, are the edges of the dual ribbon graph. And I'll do an example here, and I think just to save some time, I'll just give you the Ag invariants. Okay, maybe I'll do it on the next page. Okay, here is the surface. We have 1, 2, and then 3. And then the dual graph is given by this. And this is exactly the geometric model. And this is also exactly the data you need for the Ag invariant. And then the Ag invariant is just given by these two tuples. Okay, so you can sort of check it, and if you know how to construct it, you can check that hopefully I did my calculations right. Okay, so the Ag invariant is not a complete invariant. So there's a paper by Claire Amiot where there's a nice example, but I'm sure there are many others. Namely, in the torus, she shows that, okay, so the torus with one boundary, that there's two genter algebras, and she explicitly gives these, such that the genter algebras A and B, such that the Ag invariant of A is equal to the Ag invariant of B, but the bounded derived, I mean, the algebras are not derived equivalent. Okay, so this is what the Ag invariant tells us. 1 second, please. On the other hand, it follows from the work in Haiden, Katzarkov and Kontsevich that if we're given the surface, the stops, and a line field, and then we have a second surface which we call SB, MB, and eta B and eta A, and which corresponding to graded gentile algebras A and B. And if we suppose that the surfaces are such that there is a homeomorphism phi that goes from SA to SB, which then restricts to a bijection for the stops, restricting to a bijection from MA to MB, and such that if we pull the line field of A onto B, then that line field on B is homotopic to the line field we started with on B. If that's the case, then the two Fukaya categories are equivalent, and hence the gentile algebras are derived equivalent. So in particular, of course, if the two line fields eta A and eta B are such that A and B are zero graded or trivially graded, then we get automatically that the two algebras are derived equivalent. Okay, so for two gentile algebras, I mean, for two sort of coming from surfaces, we have a criterion maybe, but somehow that doesn't give us a criterion going in the other way. If the derived categories, if they're derived equivalent, it's not clear that we have that same information on the surface. Okay, so then this leaves the questions. What about the converse? And then, of course, also the this construction is just for gentile algebras of finite global dimension. So we also can ask, what about infinite global dimension? Okay, so maybe now is the time to say something about these line fields. Okay, so this is then the next section, which maybe is 3.1, line field of a gentile algebra. Okay, so I want to sort of give a definition, but it's not really a definition. I mean, the line field is well defined. So this is simply a section of that projectivized tangent bundle. So let that be a line field. But then I want to sort of give you an idea of the winding number of the line field. It can be very formally defined with the fundamental groups of the surface and the tangent space, but I don't think that's particularly insightful unless you work with these things a lot. So I think getting an intuitive definition is probably preferable here. Okay, so we have that line field and gamma, a closed simple curve. Then the winding number which we denote by omega eta of w of gamma with respect to the line field eta is given as follows. So we take a point on the curve and move it in the counterclockwise direction along the curve. Okay, when we do that, then the line field, or the line at Q, so at Q, remember the line field picks out some line at Q, then that line also moves along the curve. So eta Q is a line. So maybe I should do it like this. Eta Q will move, but it will also rotate during this motion. And when we get back, to Q, so if we've done a full circle or to follow the closed curve exactly once, eta of Q is also back in the same position up to a half rotation. Now the winding number is counting the number of half rotations in the clockwise and anti-clockwise direction. So so eta Q will have made several half turns or U-turns. By that I mean rotation by pi. And the line field eta, the winding number of the line of gamma with respect to the line field is the sum of these half terms, counting in the following way, counting +1 if half turn in the counterclockwise direction and -1 if the half turn is clockwise. Okay, so I think the best thing to do is to look at an example. Okay, so let's take a disk. And on that disk, I would like to draw a line field. And no, actually, let's take an annulus. Okay, and let's do a line field here. So the line field is kind of given by its foliation, where we indicate what these lines in the tangent bundle look like. And then I have one more thing to do. And okay, oh, okay. Okay, so it's yeah, you get they shouldn't be crossing here. I'm sorry. So this shouldn't be crossing. So please, if you draw it more carefully, don't have your lines crossing. Okay, so now we choose a curve in here. Okay, it goes in this direction, and we choose some starting point Q on this curve. Okay, so now, I mean, I can't show you because unfortunately it's not a blackboard, but take your pen, and this idea really comes from Claire, but I like it a lot, so Claire Mew, so I'm going to adapt it. And you start your, so maybe if I indicate it like this is the closed curve, you start here. And then if you hit something on the line field, you go and continue, and your pen is going to turn like this. And if we go, then the first thing we're going to hit is a counterclock. Now it's a clockwise rotation. So if we here follow in the direction, so we have this is equal to first, I said the first rotation is clockwise, and clockwise we have to do -1. And then we continue, and the next one we have is counterclockwise, so we get +1. And so the winding number is here 0. So maybe I should write it so you can try it. So first clockwise, followed by counterclockwise. Okay, in the slides, I have done another example so that you can sort of check out whether you sort of see how to calculate these winding numbers. I'm going to sort of stop at one here so that we don't spend too much time drawing foliations. Okay, so then there's a result by Chillingworth that can be adapted to line fields that says the following. It says that two line fields are homotopic if and only if, oh, I should name the line fields. Let's name them eta and eta prime. If and only if they have the same winding number on any closed curve, for any simple closed curve, gamma. Okay, and why is this of interest? Well, if you go back to what I said about what follows from the HKK paper, is that if we have a homeomorphism that induces homotopic line fields, then we get an equivalence of the corresponding Fukaya category. So somehow we have to be able to identify when two line fields are homotopic. And we can do that by that result of Chillingworth by their winding numbers. Okay, so we have to understand these winding numbers of the surface. And yeah, you'll see in the example, in the other example I put in the slides, we get non-homotopic line fields. Okay, so a note, which I think I have already said, but let's state it again. A line field, eta on the surface as A, where A is a Genta algebra, defines a grading on the Genta algebra A. Okay, and so with Claire Amiot and Pierre-Guy Plamondon, we looked at Genta algebras that are ungraded, so in some sense they have a 0 grading. And then we found a particular line field for which we can define simply on the polygons and then glue it together from from these different polygons and get the line field on the whole surface, such that we can actually describe the winding numbers, and this line field will give us that zero grading. So now we start with a Genta algebra, which is trivially graded, and the geometric surface model, so the surface dissection of a Genta algebra A, so no grading. So then define a line field eta A by setting for each polygon. Of course, we have to define in the polygon the line field such that you can actually glue and get a line field on the surface. So we use the red polygons. And here we take the line field that's tangent to the red arcs and hits the boundary segment transversely. Okay, so for each red polygon, we define this line field, i.e. tangent to the internal red arcs. So these are the edges. These are the edges of the dual ribbon graph, and transversal to the boundary. I should say that this is the sort of orthogonal line field to the one I think that's used in Haiden, Katzarkov, Kontsevich. Nevertheless, for this line field, we can then show that for any simple closed curve, gamma, the winding number of the line field is actually equal to this combinatorial winding number, which we have gotten from the geometric model. So I'll show you in a minute. So this is the combinatorial winding number. Number defined in the talk 2 in terms of left and right of the black mark points when we cross the red polygons. Okay, so furthermore, this line field here gives rise to zero grading on the Genta algebra, and eta is the unique such line field up to homotopy. Okay, so let's do an example and convince ourselves, and let's take again the example we had, but maybe I should redraw it because it was so terribly drawn. Okay, so that was the annulus. And then on the annulus, I had these red marked points. And then I had this, and I think if I remember right and see it here, this corresponds to the Genta algebra that is like this. Okay, so then I have black mark points in between the red mark points. And then you can draw the line field. Now we use this idea up here. So inside each polygon, we draw it so that it's transversal to the boundary and tangent to the red edges. So you get here you get the line field like this. And then, of course, here you go tangent to this. Oops. Well, okay, so it's not completely transversal, but you get the idea. And this we have calculated. Okay, so we had the curve in here. So that was our curve gamma. And then we did just calculate that with exactly this line field we had, if we start at a point P, Q here, so let that maybe be Q, then this was given by -1 + 1 is equal to 0. And now if you remember the combinatorial winding number, well, you start and you always go from one intersection of the red graph along the curve to the next one, and then you check whether your black mark point is on the left or on the right. And here it's on the right, and I think when we said it's on the right, we do -1, and then you go from the next intersection to sort of the next two intersections. You check if in the orientation your mark point is on the right or the left, and here it's then on the left. So we do +1 by our convention, that gives you 0. So certainly in this example, it checks out, and you can check that it's true in general. Okay, so now that we have sort of translated the winding number into our geometric model, then there's maybe a chance that we can actually get something about derived equivalences. And this is the fact, and I think that's really very neat, because we do that really by using representation theory, namely through the description of the tilting complexes in terms of the geometric surface model. And they are precisely the formal generators for the partially wrapped Fukaya category. We will see. Okay, so first, I guess I'm just briefly going to recall what a tilting complex is. So if lambda is a finite dimensional K algebra, a complex X in KB Prosh, no, not A, but lambda, is a tilting complex if we have two things, namely there should be morphisms from X to itself only in degree 0. So for any shift, positive or negative, this home space should be 0. And we want X to generate KB Prosh, the homotopy category of bounded complexes of projectors. Okay, so then what is this? What are the tilting complexes in the surface? Oh, what do they look like? So this is, again, joined with Claire Amiot and Pierre-Guy Plamondon. Okay, so we have A gentle and the surface model. With the stops, with not the stops, the black mark point and the punctures, the red punctures. Then we start with T, a tilting complex. then T is isomorphic to a direct sum of complexes of the form P gamma I Fi. Remember, this is how we indexed our indecomposables in the surface, where gamma 1 up to gamma n is a surface dissection into polygons of the form, well, what are those polygons? Well, either they are, and I'm going to not use black because the black dissection is the one associated to A. So this is now a new dissection, but still it cuts the surface up into polygons. And each of these polygons is either of this form, and then it must have a red mark point on the boundary, or it's a polygon that has no boundary component, and then it has a mark point in the interior. So if you remember, these are exactly the ones that we get in Haiden, Katzarkov and Kontsevich to get formal generators. Okay, so let's do an example. Yeah, I have time for an example. Okay, so let's take our favorite algebra, A, B, and we of course know that this is derived equivalent to the algebra where we have a relation here. Or maybe I should call that A prime, B prime. Okay, so, but this is the algebra we start with. So what is the surface? We've drawn it many times. So now we want the surface in terms of the black graph here. But we do want to write down our red marked points. Here we 1, 2, and 3. Okay, and now we have a tilting complex given by the following. So T is given by the homotopy string A -1, 0. And you can amuse yourself to maybe write out what complex this corresponds to. And P, oh, this is a projective in 3. Well, okay, so maybe I should say P E3 -2. Okay, so then this is a tilting complex, and this tilting complex can be seen on the surface. And I'm going to write, oops, this is not what I wanted to do. Here, I'm going to write it in purple, maybe a bit thicker. Can you see that? Okay, and now let me draw this complex on the surface. We get this, this, and this. And if you now just look at the purple graph, then you see that it cuts up the surface into polygons, where each, here a polygon, here a polygon, here a polygon, and one big polygon here. And each polygon has exactly one red mark point on the boundary. Okay, and then we get the following corollary. Oops, I misdeleted an edge. Okay, so we get a description of those surface dissections that give us tilting complexes. So it's in some sense a converse. Okay, so we obtain a characterization of tilting complexes in the derived category in terms of appropriately graded and surface dissections. So we already know what the surface dissections look like, namely they cut it into polygons with just one right mark point. And then the appropriately graded, I'm not going to define it, but I can maybe tell you what it means. So if we draw on this surface the dual graph, then what we do is that at each marked point, we check the purple edges going away, and if there's one edge, then there's you can choose any grading, and that if we choose this grading, this induces a grading here, and then we check for this mark point that all the edges starting at this mark point here have the same grading as this. So the gradings have to be equal. At the first intersection point with the dual graph. And if we have this grading here, then this induces a grading here. And then we have to check that all the edges connected here, when they first intersect with the dual graph, they have the same grading as that one here. And if they're all the same, then, I mean, for each of these boundary vertices, then we get a tilting complex. Okay, and then we can use this to give a complete derived invariant. So just this again with mu and Flammondon. Namely, okay, so A and B are gentle with associated model SA, comma A star, the dual graph, the marked points, and SB dual graph, marked points. Then A and B are derived equivalent if and only if there is an orientation preserving homeomorphism phi that sends SA to SB with the conditions that it sends the marked points to the marked points and the line field to a homotopic line field. So it's exactly, we get exactly the converse to the Haiden, Katzarkov and Kontsevich and extend it to infinite global dimension. But actually we also give an algebraic proof of both directions for this result. But let me finish writing it. Sending MA to MB and such that for any simple closed curve comma the winding number is equal of the curve of the curves are equal. And of course, this really means because by chilling, I mean, we know that this winding number here is the winding number of a line field, and by Chillingworth, we know that this means the line fields are homotopic. Okay, so I would like to finish with a remark. Namely, the remark I would like to finish with is that it's hard to determine whether such a phi exists. And we do in APS give a numerical criterion in terms of the combinatorial winding numbers and a generating set, or a special generating set of the fundamental group of the surface. And this criterion we give is based on a numerical criterion. Characterizing homotopic line fields. And this criterion was then given, this numerical criterion, in Likely and Polishuk. And it's clear that that the idea of Likely and Polishuk was to show exactly this result here. But I suppose in some sense we really need the algebra and the representation theory to show it. And conversely, I guess people probably have been looking for derived invariants for Genta algebras, and it really seems that there might actually, the geometry might be necessary. At the moment it is, but I don't know how much more generally this is true. Okay, so this is what I wanted to tell you, and I hope you could get something out of it. And thank you very much for listening.
So let's thank Sibylle for this very nice talk and a nice lecture series. I saw that there was at least, there are 2 questions in the chat.
Oh my God. Oh, thank you very much for that chat. Ah, Sasha. Oh, I can't believe it. Yes. Okay, let me share the screen. This is terrible. Yes, absolutely. Thank you. I'm really sorry. I meant to do that and I completely forgot today. Thank you. Yes. Okay. Okay, hold on. Let me do this. Okay. Oop. 1 second. Okay. Can you see my screen?
No, it just says you started screen sharing. Maybe if you try again. Or...
Let me try again. I'm sorry. I can't believe I forgot this. I'm really sorry. Okay.
Yeah, that's good.
Okay, good, excellent. So okay, so this here was also in a paper by Sebastian Oppe, and it was really very unfortunate because we had worked with him and then we somehow, I guess how life is, we stopped talking, and it turned out he was working on exactly the same thing, and the 2 papers came out at roughly the same time. So one of the directions of the proof that Sebastian gives is very similar, and the other direction is quite different. And actually in his paper, he does much more. He does really nice things. He shows that the spherical objects that give rise to spherical twists correspond to Dehn twists around boundary components. So it's a very nice paper and I highly recommend it. And I apologize to Sebastian that I didn't mention it, and thank you, Sasha, for pointing it out. Really, yes. Okay. Okay. What is gentle about these algebras? Matthew, do you want to elaborate? Oh, no, I don't understand what you mean. I guess that is their name, and they arose as iterated tilted algebras of type A and type A tilde. That's how I think they first came to be considered. Oh, and I don't know. So I guess the person to ask is Ibrahim Asim or Andrei Skowronski. I think they came up with the terminology. but I mean, once you start working with them, you can see why they're called gentle, because anything you want to try works for gentle algebras, and you can understand it. And it's generally not true for any other algebra except maybe type A or Nakayama algebras, I guess. Yeah. Okay, inside 2, when some decay has no stops on the boundary, does one still have a relation between AL and some derived category of the gentle algebra one can associate to the dissection? Yes. I think actually, I think so. Yes, I think in the Haiden, Katzarkov, Kontsevich, they do show that you still get a gentle algebra if you, but it has higher multiplication. So in some sense, yeah, it's an A infinity version. But if you forget about the higher multiplication, then you just get the gentle algebra. But if you have generators that cut out something that doesn't have a stop on the boundary, then you do get higher multiplications.
So there was this nice description of the tilting complexes in terms of surface dissections. Can you describe mutation of tilting complexes using something with the surface dissections?
Yes, so that I'm doing that currently in joint work with Wen Chang, and yeah, it's and I mean, yes, you can. Yeah, so oh, okay, so Daniel and Gustavo have a chat, right? But how about the existence of some derived equivalents? I don't know.
Maybe I can, yeah, just answer quickly to Daniel, maybe interest others. So you get the derived equivalence between the partially wrapped Fukaya category and the perfect derived category of that A infinity algebra that now has this this multiplication. So that's what they prove in HKK.
All right, thanks.
So are there any other questions or comments? You can feel free to unmute yourself if you, yeah. Well, if not, then let's thank Sibylle once again. And then we will move over to Gathertown for a socialization session. So Jenny posted a link in the chat. So the password is Fukaya with a small f. Yes, so see you all there.
Yeah, and then just to come one that remember that on next week we are meeting on Big Blue Button.
Yes, yes, thank you. Yeah, so we will change the program for this talks the next week. So we use Big Blue Button. So,
second, that the notes and videos are being updated in the winter school website.
Yes.